Hey everybody, doing a redox titration today, talking about it in an acidic medium using iron and permanganate. I'll discuss that in a second, but first shout out to University of Oregon for creating a wonderful simulation. There's tons of them on their website at pages.uoregon.edu, and if you're just go and check that out, there's lots of other things that might help you in your chemistry journeys. So in this system right here, we're talking about iron 2+ and a permanganate ion. This is already a balanced redox reaction, so there's no worry to make the half reactions happen for us today. We already know how to do those. But what we're showing here is we need to figure out what this concentration of iron 2+ is. I know I have 25 milliliters of it, right? But I don't quite know what the concentration is. So we have an unknown M, or molarity. We don't really know what the concentration is here. And we use a known concentration, so in this case here the molarity of my permanganate solution is 0.1618 molar. So right here this is 0.1618 molar, and I know that. I know that this permanganate exists in this molarity. We can use this equation here to do some stoichiometry with some solutions as well. But really what's happening, and if you were to excuse my poorly drawn beaker here, we're going to have some iron 2+. And if you'll notice, manganese is going from a +7 oxidation state here to a +2. So it's getting reduced. Iron is going to be throwing electrons at it. So as we add MnO4, and remember that MnO4 is purple, right? So as you can see in this tube here, it's going to be giving electrons to this MnO4, so this permanganate, and it's going to be creating Fe3+, right? So the lost oxidation state for iron, and then it's going to be creating Mn2+ by itself. Now, an interesting fact about this is that Mn2+ is colorless. And maybe I could draw that a little bit better. But so this is colorless, give you the Canadian spelling. And so when manganese 2+ ions are in here, after they've been reduced by iron, they become colorless. So it will continuously be colorless down here in our beaker. What happens though when we reach what's called the end point is that once there are no more iron 2+s that exist inside this beaker, so let's say that all of them now are iron 3+, and they don't have any reducing capabilities. This is no longer a reducing agent. It doesn't have the electrons to give away. So if I add one more drop of MnO4, what's going to happen is that MnO4 is just going to sit in my beaker. And remembering that this is a purple color. So my whole beaker will have a slight tinge of pink once I add one last drop, or maybe a little purple color. And that means that I've reached what's called the end point. Okay? So end point of my titration. So I know the volume of the MnO4 that I've added, the permanganate that I've added. And if I know the volume of permanganate, that means I can know the moles, and if I know the moles of this using molar ratios, I can figure out what the moles of iron was. So ultimately, we're using some solution stoichiometry and a bit of redox know-how to figure out an unknown of a metal in this case. So what we'll do, and this is much like the lab that you're going to be taking on Monday if you're in my class, if you may have already done this if you're in a different class. And so what we'll do is we'll actually go through the simulation. Now you'll add your volume of potassium permanganate. Now remember, I just need to remind you guys that even though we're dealing with KMnO4, remember that that's aqueous, and they're going to break into their charges of K+ and MnO4-. And this potassium plus is a spectator ion, so we don't really deal with it too much. As you can see here in our written equations, we don't have potassium in there. So that, if you were confused as to where that K came from, where the potassium was coming from, that's just to give you an idea of where that went. So here, if I add my potassium permanganate, and you have to be careful when you do this, so you don't want to add too much at the beginning because then you won't be able to detect when the iron stops oxidizing and stops reducing the permanganate. So here I'm adding them bit by bit. Once the color starts to change and hold, there, so as soon as you see that flash of purple and then it dissolves back into the solution, you will continuously add them what's called dropwise. So keep continuing to add drops and drops and drops of your potassium permanganate. And as I do this here, Noticing that we still stir, right? So as you're stirring or swirling your Erlenmeyer flask, you're making sure that all of the available iron 2 pluses are actually meeting up with the permanganate solution. So here we're just waiting for these dropwise bits to go over. And what you'll do to get dropwise happening in your burette is you'll twist your lever here just ever so slightly, so that way you're getting little bits of drops at a time. And of course, if you'd like to speed ahead in the video until this turns completely pink, I think that that would probably be a good thing for you. Otherwise, I don't even have any jokes to fill this time with. I'm kind of just holding these things in dropwise. What you'll notice in the lab is that you will grow impatient with this, but the main thing is to stay calm and make sure that you're paying close attention to the water, so that way you know when it's going to turn pink. That way you'll have less human error and you'll be able to decide what the proper concentration is. So again, fast forward. Oh, and see, I was talking through myself. So I added one too many drops, and you'll notice here that my solution has turned a nice bright pink. So judging up by here, I've noticed that my total volume of potassium permanganate that I added is 35.12 milliliters. So here I know that I have 35.12 milliliters of MnO4 minus. Now I have a molarity as well of potassium permanganate. So I know that I can take this and multiply it by the molarity and get moles. So here I'm going to take this and I'm going to change it quickly into liters, so that way we know that we're dealing with 0.03512 liters times, and of course in IB we call these decimeters cubed, and so this is going to be 0.1618 moles per single liter, right? That's where I'm getting this number from. My liters will cancel, and I'll pull out my calculator, and so I'll have 0.03512 times 0.1618, and that's going to give me 0.00568. So this is 0.00568 moles of MnO4 minus. Great. And so I need to take this number of moles, and I need to figure out how many moles of iron that must have reacted with. So remember that this is a 1 to 5 ratio. So I'm going to take my moles of permanganate, 0.00568 moles of MnO4 minus. And so I'm changing that into what I want. So I have 5 iron 2 pluses here for every one single permanganate ion that I have. We'll cancel those out. And so if I take this number and I'll multiply it by 5, that should give me 0.0284. So 0.0284 and 0.0284, yeah, let's just call it that, moles of Fe2 plus. Okay, so that may be the end of the question, depending on what it's asking for you. Some questions will say how many moles, some questions will say what was the initial concentration. So here we're actually going to be doing the initial concentration, and so the concentration is going to be, we had 25 milliliters in our beaker to begin with. So remember that the molarity is equal to the moles per liter. In this case here I had 0.028 moles, sorry, 284 moles. And my screen keeps unextending on me, so bear with me for a sec. 0.2884 moles. And that's all divided by my 0.025 liters. And so here, if I were to take that and divide it by 0.025 liters, that's going to give me a concentration of 1.13 or 1.14. Let's round that up. So 1.14 molar. Now, for you, for your homework, I would love it if you could do the simulation and actually put your answer in here click OK, and you'll notice that you're correct, right? So this actually has a built-in check system. So if you can get the number of milliliters, do your calculations, and then put your molarity final calculation in there, you'll notice that you did it right or not. So this means that the unknown iron concentration is now a known iron concentration based on our analysis, and that it has 1.14 moles per liter of iron 2+ inside this beaker. And we did that by knowing a concentration of potassium permanganate, using some redox knowledge, and using a little bit of solution stoichiometry. Thanks for watching, and I'll see you soon.